Hello, everyone. Today we're going to dive into the fascinating world of AI agents. Our discussion will cover what AI agents are, how they've evolved over time, the mathematical and architectural principles behind them, and how they integrate into modern data science and real-world applications. Let's get started. Before we jump into the details, here's a quick overview of what we'll cover. We'll start with basic definitions and characteristics of AI agents, explore their historic evolution, dig into how they work, both in terms of architecture and mathematical modeling, and then examine some advanced topics like multi-agent systems and real-world applications. Finally, we'll look at some of the current issues and challenges in the field before wrapping up with a summary and discussion of future directions. Let's begin with the fundamentals. So what is an AI agent? At its core, an AI agent is an autonomous entity that interacts with its environment through perception, decision-making, and action. This means that it isn't merely following a predefined set of instructions, it actually adapts over time. The key characteristics here are autonomy. The agent makes its own decisions. Adaptability. It can adjust to changes in the environment. Learning capability. It can improve its decision strategies based on experience. As we proceed, keep in mind that while the underlying algorithms might be complex, the central idea is to create systems that can act intelligently in dynamic contexts. Now let's take a look at the history of AI agents. In the 1950s, with the foundational work of Alan Turing. Turing not only proposed the idea of machine intelligence, but also introduced the famous Turing test, which set early benchmarks for what we might consider intelligent behavior in machines. In the 1960s and 1970s, research expanded into rule-based systems and expert systems. These early explorations laid the groundwork for more autonomous reasoning. During these decades, experiments in robotics and early symbolic AI hinted at behaviors we now recognize as agent-like. In the 1980s and 1990s, things really began to take shape. Agent architectures started emerging with systems such as SOAR and ACTR, which provided structured ways for agents to perceive, reason, and act. This era also saw the introduction of formal models for rational decision-making. One of the key frameworks from this period is the Markov decision process, or MDP. The MDP is defined by the term SAPR gamma, where S is the set of states, A is the set of actions, P represents the transition probabilities, R is the reward function, and gamma is the discount factor. This framework helps formalize the decision-making process, and we even see its influence in the Bellman equation, which helps define the optimal value function. Then, moving into the 2000s and today, the modern era, advances in reinforcement learning and deep learning have dramatically enhanced the capabilities of AI agents, leading to their integration into multi-agent systems and applications ranging from autonomous vehicles to cybersecurity and even game AI, as exemplified by systems like AlphaGo. Let's now focus on the core components of an AI agent. Fundamentally, these agents rely on three primary components. Sensors. These capture data from the environment. Think of them as the agent's way of seeing or sensing what's happening around it. Actuators. This is how an agent affects its environment, the means by which it executes actions based on its decisions. Cognitive architecture. This is the brain of the agent. It processes the data from the sensors, decides on a plan of action, and then uses the actuators to interact with the world. Let's delve a little deeper into the mathematics behind agent decision-making, specifically through the framework of Markov decision processes, or MDPs. An MDP provides a way to model decision-making where outcomes are partly random and partly under the control of the agent. It is defined by the tuple S, A, P, R, gamma, S, the set of possible states, A, the set of possible actions, P, the transition probability from state S to state S prime when action A is taken. R, the reward function indicating the benefit of transitioning between states. Gamma, the discount factor, which essentially prioritizes immediate rewards over future ones. The central idea here is captured by the Bellman equation. This equation underpins many dynamic programming and reinforcement learning methods used in data science. Now, let's connect the theory to practice with reinforcement learning, a key method used to train AI agents. The goal of reinforcement learning is to maximize cumulative rewards over time. The agent follows a policy, a mapping from states to actions, which it iteratively refines. The value function represents the expected cumulative reward from any given state. A common learning algorithm is Q-learning, which updates the expected value for a state-action pair as shown. This update rule allows the agent to learn from interactions with the environment and progressively approach an optimal policy. The slide also includes a placeholder for a diagram that visually represents the reinforcement learning loop. As we push the boundaries of AI, it's important to recognize the shift towards multi-agent systems. These systems consist of multiple AI agents that interact with each other, either cooperatively or competitively. In these systems, several challenges arise: coordination and communication. How do agents share information and work together? Learning in non-stationary environments. Since other agents are learning and evolving simultaneously, the environment isn't static. Conflict resolution and cooperation, balancing competitive and cooperative strategies. Many of these challenges can be addressed through game-theoretic approaches, such as finding Nash equilibria, which help us understand and predict the outcomes of these interactions. Now let's take a look at some real-world applications of AI agents. Their role in data science extends to various domains, including autonomous vehicles, where real-time decision-making is critical for navigation and safety; robotics, enabling automated task execution and manipulation in dynamic environments; intelligent personal assistants, handling natural language processing and user interactions efficiently; finance and trading algorithms, making high-stakes decisions under uncertainty. Each of these applications leverages the principles we've discussed today. Now let's explore how AI agents integrate into data science workflows. Automated data workflows. First, AI agents play a pivotal role in automating data workflows. They handle tasks such as data cleaning, feature engineering, and even model selection. By automating these repetitive yet critical steps, data scientists are freed up to focus on high-level strategy and complex analysis. This not only accelerates the data pipeline, but also reduces the likelihood of human error in pre-processing steps. Interactive analytics. Next, consider the concept of interactive analytics. AI agents can serve as virtual assistants that query databases on the fly and generate dynamic visualizations. Imagine a system where you simply ask for a trend analysis, and the agent returns an up-to-date chart. This level of interactivity supports real-time exploration of hypotheses and iterative analysis, which is indispensable in a fast-paced, data-driven environment. Federated and collaborative learning. Another key integration is through federated and collaborative learning. Here, AI agents enable secure data sharing across disparate sources while ensuring sensitive data remains local. This is especially important in scenarios where data privacy is paramount, such as healthcare or finance. By using federated learning, AI agents allow institutions to collaborate and benefit from collective insights without compromising on privacy. Tool integration. Finally, AI agents are designed to work alongside established analytical tools like Python, R, TensorFlow, and others. This integration streamlines the data science pipeline, combining the strengths of these tools with the decision-making and automation capabilities of AI agents. Overall, this synergy enhances efficiency and allows for more scalable and robust data analysis processes. Visualize this integration as a pipeline where data flows through each stage, from acquisition to pre-processing, through analysis and visualization, guided by the intelligence of the AI agents. Now let's discuss some of the benefits and real-world applications of integrating AI agents into data science. Enhanced efficiency. One of the strongest advantages is enhanced efficiency. By automating routine tasks, AI agents allow data scientists to focus on solving more sophisticated problems. What this means in practice is faster turnaround times on projects and the ability to quickly iterate on models and analyses. Real-time, scalable insights. AI agents excel at managing large datasets and delivering rapid insights. In areas like cybersecurity, where data is continuously streaming and conditions can change rapidly, the ability to process and act on data in real time is critical. This scalability ensures that insights remain timely and relevant, regardless of the data volume. Optimized decision-making. Another important application is in optimizing decision-making. AI agents use methods such as reinforcement learning to constantly refine their recommendations. For example, using a Q-learning update rule allows an agent to incrementally improve its performance by learning from every decision it makes. This continuous optimization is crucial in complex analytics, where small improvements can lead to significantly better outcomes over time. Democratizing data science. Finally, AI agents help democratize data science. With routine analysis being automated, advanced data science capabilities become accessible even in under-resourced environments. This broadens the impact of data science, making it possible for more organizations to leverage high-end analytics without needing a large team of specialists. In essence, AI agents are lowering the barrier to entry across multiple industries. As with any evolving field, several challenges remain. In the realm of AI agents and data science, these include scalability. How do we extend agent frameworks to manage increasingly complex, large-scale environments? Interpretability. Enhancing the transparency of these systems is essential, especially when used for critical decision-making. Ethical considerations and safety, ensuring that agents are deployed responsibly and securely. Coordination in multi-agent scenarios, effectively managing and predicting the interactions among multiple dynamic agents. To wrap up, here's a summary of what we've covered today. AI agents are autonomous systems that blend perception, reasoning, and action. They rely on mathematical frameworks such as MDPs and learning processes like reinforcement learning in order to operate effectively. We explored their historical evolution from early rule-based systems to modern deep reinforcement learning, and looked at how these principles have been applied in multi-agent systems and diverse real-world applications. Looking forward, future research will need to concentrate on issues like scalability, better interpretability, ethical deployment, and more sophisticated multi-agent collaboration methods. These advancements will not only deepen our understanding, but also broaden the practical impact of AI agents in data science.